Okay, hello everybody. This is the second of several videos that we are making for the Newlane Symbolic Logic project on Cantor and Gödel. My name is Vladan Djordjevic, and Professor Blair is also with us or nearby. So, Professor Blair, feel free to get involved whenever you feel like it. In the previous shorter video, we had an introduction, and I tried to give you a hint about some philosophical topics related to the notion of infinity, because this is what is Cantor's main topic. And I try to give you a hint of why infinity proves to be very difficult. It seems that our cognitive abilities are not made for that notion. We cannot imagine infinity. We cannot touch it, smell it. All we can do is examine some finite things. And when we try to apply our generalizations about finite things to infinite things, then the trouble begins. We easily fall into contradiction. It took lots of time. Late in the 19th century, Cantor proposed the first consistent formal theory and helped people talk about infinity and the related notion of continuum in a consistent way. The fact that it was so difficult to come up with such a theory does not mean that your task will be difficult, because it does not mean necessarily that the theory has to be difficult. Remember, Newton's physics, considered to be the most successful science in the history of science, was of course very difficult to develop, but we learn Newton's laws in elementary school. They were simple enough so we could do it as kids. And Cantor's theory, maybe it's not for elementary school, but still it's beautifully elegant and simple enough for us. And these are some notions that we will mention today. It's a theory of infinite sets, and Gödel also uses the notion of sets. So let us start with that notion. We need to be clear about what sets are there. That notion is similar, but not quite the same as a class, collection, or a group of things. A set is something over and above its members. It is defined by its members. So what a particular set is determined by the members. But the set itself is an entity different from the members, which is not necessarily true of collection or group of things. These are ordinary language words. We can define them and use them as technical terms, and there is opposite to set, Mariological term of a Mariological sum, which is not anything over and above its members. It is not a different entity that is somehow different from the members. For the set is a different entity. It's something over and above its members. And what could the members be? Anything whatsoever. concrete things that exist in space and time or abstract things. So we can think of a set containing myself, a dead volcano on Sicily, number pi, and aesthetics. Nothing prevents us from creating such weird sets, although practically it's more useful to have something that connects the members. There can be a property so that the set collects all and only things that have the property. That seems to be a good and practical way to define sets. And indeed, Frege at one point believed that set theory could be made that way. A property could be, for example, a number being larger than 10, less than 20. Or we can, instead of listing all the numbers, which is not practical if there are many of them, instead of listing all the members, we can pick them by the property that they all satisfy, like a set of writers. Or we can have a set of barbers that do not shave themselves, and so on. Again, a set is a single entity and is different from its members. The set of all philosophers is not itself a philosopher. The set of all philosophers is numerous, but no philosopher is numerous. There is a proverb in philosophy that we owe to Quine: no entity without identity. So we do not have a full definition of an entity unless we can define its identity. So we need a few more words about the identity of sets. Two sets are identical if and only if they have the same members. If and only if means that we have a biconditional implication from left to right and from right to left. In one direction, this criterion of identity is trivial. From left to right, it's trivial. And the other one, it is informative. From right to left, it tells us that the sets I'm going to mention are the same. I hope that you can see my mouse hovering over A and B and some curly brackets. Curly brackets are a standard symbol for a set. So what's between the curly brackets are the members of the set. So here where my mouse is, we have a set AB. Then there is a set BA and a set containing AAAB. According to our criterion of identity, these are identical sets because the order is not important and repetition does not count. We could have decided otherwise, but this turned out to be practical and good for our purposes. We do need ordered sets, and there are ways to define them. We use them all the time in mathematics, in logic, and wherever these are applied. But the basic sets are defined in such a way that the order is not important. We also need a notion of an empty set, and I'm hovering over the symbol that is used for an empty set. We said we can define sets using a property of the members. So we can define an empty set deliberately or by accident that has no members. For example, we can talk about the set of unicorns in my room here, or the set of queens and kings of the USA, and they turned out not to have any members. It is a consequence of our convention about identity that all empty sets are the same. So the set of unicorns and the set of queens are the same.
That is the set of unicorns and the set of queens in America?
Yes. We need a notion of a subset. So a set is a subset of another set if and only if all the members of the first are also members of the second. This means that a subset is equal to the main set, or it can have fewer members. The consequence of our definitions is that an empty set is a subset of any set. Another consequence is that each set is a subset of itself. Again, about terminology. Plato is a member, but not a subset of the set of philosophers. The set containing Plato and nothing else is a subset, but not a member of the set of philosophers. And the set containing Plato and Aristotle and nothing else is a subset of the set of philosophers. One more definition, a proper subset. A proper subset is smaller than the basic set. So we can say that a set O is a proper subset of a set S, if and only if O is a subset of S, and some members of S are not included in O. So proper set is always smaller than the basic set in the sense that some members are missing. Cantor was interested in infinite sets, in particular in the sets of numbers. And people had their intuitions about such sets. They're infinite, but obviously there are larger and smaller infinite sets. For example, a set of odd numbers is obviously smaller than the set of all natural numbers. How much smaller? Well, it seems 2 times. Now you can see how the terminology that we developed for finite things become weird the moment we try to apply them to infinite sets. So what would be the meaning of an infinite set being 2 times smaller than another infinite set? Because infinity times 2 is infinity. What's the difference? So Cantor help us put some order into these claims and intuitions. He asked himself, how would we count and say that there is more of these things than another group of things if we had no language and if we knew no numbers? Also, what do kids who use their fingers to count things, what do they do? It seems that they compare. Are there more dogs than cats in my room? So let's say I have 2 of each. Then it seems that they can put one next to each other, one cat for one dog and the other way around. And then it seems that there's the same number of them. And in terms of sets, those sets of cats and the set of dogs would be the same. We have in mathematics the notion of a correspondence 1-to-1. And applied to these 2 sets, it's very convenient for dancing. Everybody would have a pair. So for each guy in the left set, there is exactly one lady from the right set and the other way around. For each lady, we have exactly one gentleman. And we call that one-to-one correspondence. Only the top left correspondence is 1-1 on this slide. The top right has psi in the right set associated to 2 members from the left set. The bottom left example, we have the heart associated to 2 members. So this is not one-to-one correspondence. The fourth example, bottom right, the heart has no associate, it's left alone. So these 3 examples are not one-to-one, only the top left is one-to-one correspondence. The idea to compare the size of sets using one-to-one correspondence and to claim that sets are of equal size if they are related one-to-one. This is an idea that works perfectly for finite sets. Cantor's idea was to apply the same criterion to infinite sets and accept whatever the consequences of that might be. This is what we need to remember. 2 sets are said to be of the same size if and only if one-to-one correspondence between them is possible. So this is the definition of 2 sets being of the same size. And this definition does not require that one-to-one correspondence is the only one possible. If there are correspondences that are not one-to-one, this is not relevant. What is relevant is whether one-to-one correspondence is possible. And to prove that it is possible, we need to define one. Before we start applying the definition, let me remind you of the kinds of numbers that we learned in school. I'm hovering now over the set of natural numbers. The usual sign for it is capital N, and it can include a 0, 1, 2, 3, and so on. Integers include the natural numbers, and they also have negative numbers. Then we have rational numbers that we get by dividing one integer with another integer. We can present rational numbers using the digital form. So this one, for example, is 5/4. And beside rational numbers, we have irrational numbers, like square roots, those numbers that presented in a digital form have an infinite number of digits. And this calls for the number pi that we use to measure the circumference and the areas of circles and so on. Okay. This is something we would expect. The number, under quotes, the number of odd numbers and the number of even numbers are the same, meaning that the sets of odd numbers and even numbers are the same according to the criterion Cantor defined, because we can have one-to-one correspondence between them. The general formula for this correspondence is 2n minus 1 in the top row and 2n in the bottom row. There's no odd number that is left without an associate in the bottom row, and the other way around, there's no even number that is left without its associated odd number. And there's no number that is associated to more than one number, which means that we have a one-to-one correspondence. Everything fine so far. And this example also is something that we expect. Natural numbers form a set that is equally big as the set of negative integers. We have an obvious one-to-one correspondence between them. The general formula is we have number n in the top row and the number minus n in the bottom row. What else do we expect? What people did expect in the late 19th century when Cantor did this, and what maybe Cantor himself expected, is that a set is bigger than its proper subset. There is a related law or axiom mentioned by Euclid, which says that the whole is bigger than the part. So we might expect that there are more natural numbers than odd numbers. However, when we look at this table, it seems that we can relate one-to-one odd numbers to natural numbers. The general pattern is 2n minus 1 is related to n. And it seems that we will never run out of odd numbers to relate them to natural numbers, and the other way around. No number is associated to more than one number, and no number is left alone. So the consequence of Cantor's criteria of the size of the sets is that these are sets of the same size, even though one is the subset of another, a proper subset of the other. That's the first exciting results that Cantor came up with. And once we have this example, we can easily think of others. Obviously, the set of even numbers is of the same size as natural numbers. We can relate n to 2n. And then we can think of other subsets of natural numbers. We can try numbers that are divisible by 5 and relate them to natural numbers. So I'm hovering over the first number above natural numbers. If we decide instead of odd numbers to use numbers divisible by 5, we would have 5 here, 10 here, 15, 20, and so on, 5n related to n. So the natural numbers are not more numerous than the numbers divisible by 5, or divisible by 8, or divisible by 1213, and so on. We can think of such examples without end. We can do this as well. Here is a correspondence that at first sight has more numbers in the top row than it has in the bottom row. But in the top row, we have the subset of the bottom row. We have odd numbers at the top, natural numbers at the bottom. and we skip every second odd number when we make a correspondence. What does this mean? Does this mean that the set of odd numbers is larger, more numerous than the set of natural numbers? Here is again the same example where we had one-to-one correspondence between the set of odd numbers and the natural numbers. And Cantor would say the second table gives us a conclusive reason to say something about the relative size, while the first table, the first correspondence defined by the first table gives us no conclusive reason for comparison. Why is that? Because the definition says two sets are of the same size if and only if a one-to-one correspondence is possible. If another correspondence that is not one-to-one is possible, this doesn't mean anything. So there's nothing conclusive in the correspondence given in the first table, and there is something conclusive in the correspondence defined by the second table. Okay, we can relate natural numbers and any subset of natural numbers. But it seems obvious that there must be more rational numbers than there are natural numbers. Because between any two natural numbers, say between 0 and 1, we have an infinity of rational numbers. 1/2 is there, 1/3 is there, 1/4, 1/10, 1/1000. There's no end. And besides that, not only between 0 and 1 do we have an infinite number of rational numbers, but between any two rational numbers, there is an infinity of rational numbers. That property of number is called density. The rational numbers are said to be dense, which means that between any two rational numbers, we can find a third one between them, larger than one and less than the other. Okay, so there are much more rational numbers than natural numbers, but let us try to tame rational numbers in some way. It seems that we cannot list rational numbers. We cannot put them in one line. Putting numbers in one line is very convenient for the natural numbers. And we say that we can list them. We can also list subsets of the set of natural numbers. We can list odd numbers very, very easily. So having one dimension to list them is very convenient. But how can we do that with rational numbers? Yes, rational numbers. Here we have a two-dimensional matrix, and it is infinite. We can extend it infinitely to the right and down, which means that we can add members in each row, and we can add members in each column. It seems that we can we can put all rational numbers in this matrix. In the first row, we have all the natural numbers to infinity divided by 1. In the second row, we have all natural numbers divided by 2, then divided by 3, then divided by 4. It should be 4/4 here, it's a typo, and so on. And it seems that any rational number can find its place here, because rational numbers are defined by two integers. To make things simpler, we talk about positive rational numbers here. For the moment, we will ignore the negative numbers. So for any rational number, we can easily find a row and a column where its place is. There are no empty places, and there is no rational number left without its place in this matrix. Good, but that matrix is not convenient for natural numbers. Each row is convenient for natural numbers, so we can list them. But we can think of a way to order natural numbers in such a matrix in a different way, not to list them in one dimension, but to somehow go around the diagonal and arrange them that way. We start at the top left corner and put the first natural number there. Then we go to the right, down, left. Again, to the right, down, left. Again, to the right, down to the diagonal, and then to the left. And so on. It seems that we can put all the natural numbers in this matrix. And let's say that I do it, that you do it, and the third person does it. And then we compare what we did. It seems that our matrices will be identical. Why? Because it's a simple algorithm that can tell us where is the place of each natural number. For each natural number, we can calculate what is its column and its row. And the other way around, if a column and a row is given, we can calculate what natural number must be at their intersection. There's no empty intersection, and there's no number that has no place in this matrix. Okay. Now let us imagine one more thing. Imagine that I can lift the right matrix with the natural numbers and put it over the matrix with the rational numbers on the left. I make sure that the rows and columns are exactly one on top of each other. So the top left corner will of the right matrix will be above the top left corner on the left matrix, and the 39th row of the right matrix will be above the 39th row of the left matrix, and so on. Why am I bothering you with these details? Because we need them to make sure that there is a one-to-one correspondence between the numbers in the right matrix and the numbers in the left matrix. Which means that Cantor came up with another amazing result, that the set of natural numbers is of the same size as the set of rational numbers, even though the rational numbers are dense. And now we said that we can easily list natural numbers, and because there is a one-to-one correspondence, as we can see from these two matrices, the further conclusion is that we can list rational numbers. So now we go back from the way we filled in this matrix with natural numbers. We will read the rational numbers in the similar way. We start in the top corner, we go to the right, down to the diagonal, and to the left. To the right, down to the diagonal, to the left, and so on. And write these numbers in one row. So here is number 6 in the second row, third column. Second row, third column is here. It's 3/2. Here we have 3/2. Number 3 is in the second row, second column. 2/2 is in the second row, second column. Here they both are. One-to-one correspondence between natural and rational numbers. It seems that we are forced to conclude that there's no other kind of infinity different from the infinity of natural numbers. Our initial intuition was that some infinite sets must be bigger, whatever that means, than other infinite sets. But whatever we tried now, we managed to make one-to-one correspondence. What about real numbers? To make things simpler, we will consider real numbers between 0 and 1. Whatever we conclude about them will hold a fortiori for the set of all real numbers. But for the sake of this argument, it's enough to have real numbers between 0 and 1. We need to agree that all such numbers can be presented in their digital form. They all look like this: 0 point and then a series of digits, which is infinite. The idea that we can list real numbers is hidden here. We put a natural number as an index to each real number. And we assume that every single real number between 0 and 1 is somewhere on this matrix. The order in which we put them is not important. So these numbers are put here randomly. Nothing in the argument depends on the particular order. We could mix them all. The argument will remain the same. Next thing we will do, we will ignore the zeros that are common for all these numbers and just look at the digits that come after 0. This is the famous diagonal argument by Cantor. Why? Because we will do something with the diagonal. I hope you see that the digits on the diagonal they have gray background. Now, we will define a real number that is between 0 and 1 in this way. Might look complicated at the beginning, but it's not. We just mechanically do whatever it says there. The number we define will be called R0. And we define R0 by defining separately each digit of R0. In general, we define the nth digit of R0 being 5 if a certain condition is met. What is the condition? The condition is that the nth digit of the number Rn is somewhere on this list by assumption. If the nth digit of Rn is different than 5, then the nth digit of R0 will be 5. Otherwise, it will be 6. Well, let us start calculating the number R0 that will help us understand this definition. So if n is equal 1, we are looking for the first digit of R0. It will be 5 if the first digit of R1 is different than 5. Where is the first digit of R1? It's the first digit on this diagonal. The first digit of R1 is 5. So this condition is not met, and the first digit of R0 will not be 5. We go to the second condition. If the first digit of R1 is equal 5, which it is, then the first digit of R0 will be 6. So it's 6 that I write here. Now, what is the second digit of R0? It will be 5 if the second digit of R2 is different than 5. Where do I find the second digit of R2? On the diagonal. It's 9, so it's different than 5. So the first condition is met. So the second digit of R0 will be 5. The third digit of R0 will be 5 if the third digit of R3 is different than 5. I look at the diagonal, there is the third digit of R3. It is different than 5. So the third digit of R0 is 5. Let us check the ninth digit of R0. It will be 5 if and only if the ninth digit of R9 is different from 5. It's here, it's 4, it's different from 5, therefore the ninth digit of R0 will be 5. So we go along the diagonal and make R0 different from the number that intersects with the diagonal. R0 can in principle have all the digits the same as R5, except at the fifth place. At the fifth place, they must differ. If R5 has the fifth digit 5, then R0 will have the fifth digit 6. If R5 has the fifth digit different than 5, then R0 will have the fifth digit equal to 5. So R0 must differ from each number that is listed, presumably in this matrix, at least at one point, at least on the diagonal. It must be different from the number whose row intersects with the diagonal. I hope that this is clear. I hope that it is clear that R0 must differ from each real number listed here. But R0 is a real number larger than 0 and less than 1. So our initial assumption that we managed to list all real numbers between 0 and 1 was false. And in whatever order we want to list real numbers, Cantor can always use this diagonal argument to define a number that cannot possibly be on the list.
So imagining on row 10 could have been in column 1 0, and then the next column 6, 5, 5, 5, 5, 5, 5, 5, 5, and then that next one, then if the next one was 5, fine. If it's not 5, fine. But either way, even if that row was all the same as this diagonal number that you had made, on that row, on that nth digit, it would have to be different. Is that right?
I think that we agree. So right, the way I filled in this matrix, we have digit 5s all up to the 9th place. It could have been different, but it turned out that we have only one digit 6 for up to the 9th place. And what happens later? We have either a digit 5 or a digit 6. For R100, in the 100th column that is on the diagonal, there will be some digit, 100th digit of R100. And the 100 digit of R0 is defined so that it must be different from the 100 digit of the number that is already in the matrix, R100. So each number will have at least one digit different from R0, at least the digit that occurs somewhere on the diagonal. Okay, let us go back to the slideshow. Let me make sure that this is what you see. Again, let us analyze the argument. Its form is reductio ad absurdum, which means that we start with an assumption, and the assumption is that all real numbers between 0 and 1 can be listed, brought into one-to-one correspondence to natural numbers. Then Cantor proved the existence of a real number that cannot possibly be on the list. However, we order the real numbers on the list. There is a real number, R0, that is not on the list. And that number is larger than 0 and less than 1. This contradicts the initial supposition that all real numbers were listed. Therefore, the supposition is false. Real numbers cannot be listed. In other words, they cannot be into one-to-one correspondence to natural numbers. Cantor will always be able to define a number that is not related to a natural number. So the set of real numbers and natural numbers are not of the same size because one-to-one correspondence is not possible. Okay, let us mention some notions that Cantor defined. And it's good to know these notions because you can see them in philosophical literature every once in a while, even in the literature that is not formal. The set of natural numbers is said to be countable. Every set that can be put into one-to-one correspondence with a set of natural numbers is also said to be countable. The diagonal argument shows that real numbers cannot be listed. In that sense, there are more real numbers than natural numbers, or the set of real numbers is bigger than the set of natural numbers. So it's an infinity of a different size. And we will find some more tidy terminology to talk about this. Now I just throw in some notions that we have from dealing with finite sets. Every set bigger than the set of natural numbers is said to be uncountable. So these are countable, uncountable are notions that you can encounter in philosophical literature and other literature that needs set theory or deals with infinity or continuum. And continuum is the notion that we will do next because it will give us an understanding of uncountability. By assumption, there is some relation between continual magnitudes and a set of real numbers. The continual magnitudes that are usually discussed in metaphysics before there was any formal theory are space and time. We say that these are continual magnitudes, which means that, for example, a straight line is such that it has no holes. A cube is a continual geometric figure, which means that there are no empty spaces anywhere within it. Time is a continuum, which means that there are no lapse between moments, or there are no empty intervals where the time does not flow. So space and time and geometrical figures are examples of continua. And what do they have to do with real numbers? There is an idea ascribed to Euclid that Euclid did not invent the idea, but it seems that he believed that it was right, that geometrical entities can be regarded as sets of points, even though points are of zero size. And those that do not like this idea of Euclid would say that a point is nothing, and you cannot get something out from nothing. Zeno is one of those who would say that way. But what is the relation between real numbers and continua? If continua is presented as a set of points, then that set is of the same size as the set of real numbers. We cannot get a continua having a set of points that is countable. It must be bigger. There should be more points to get a continual magnitude. And if it's about time, then it's not about points, but moments in time. So the analogous idea would be that time is composed of moments, which are not intervals. They don't last for a finite amount of seconds. Here is Zeno's argument that is believed to be a reductio ad absurdum of this Euclidean idea that continua can be composed of points. You know, we have only fragments of Zeno's, and most of them are not from the first hand. So this argument is not quite clear, but this is an interpretation, and what I said is the presupposed target of this argument. All finite segments, by segments, Zeno means a finite line. All finite segments are composed of an infinity of identical points. How do we know that they're identical? Well, points are defined as that has no parts. So if it has no parts, there are no parts that will be different to make a difference between them. You can buy this argument or you can disagree, but Euclid himself would accept that his points are identical. They are extrinsically different, but intrinsically there's no difference between them. So even Euclid would not question this premise. Then the other premise is a disjunction that says that points out of which we compose a segment have size either 0 or finite. The third logical possibility that points are infinite is not interesting. Obviously nobody believes that. Now we have a disjunctive premise, which means that we have a so-called dilemma with two horns. Each horn brings a different conclusion. The first conclusion with the left disjunct, claiming that points have a 0 length, is that the total length of the segment is 0. Why? Because when you add 0 to 0, and again 0 to 0 to 0 to 0, you get 0. You end up with 0 how many times you add another 0. Nothing and nothing is nothing. The right horn of the dilemma says that the total length of the segment is infinite because we have points that are of a finite length, and there is an infinity of them, as said in the first premise. So the total length of the segment is an infinite number of finite lengths, which is infinite. And this is presumably a reductio ad absurdum of the Euclidean thesis of the structure of continuum, that continuum could be composed of points. We end up with two absurd conclusions that each line is either of 0 length or of infinite length. Before we see how Cantor would reply to this argument, let us do some more one-to-one correspondences, this time between continuum. We will use geometrical interpretation of continuum because then we have some intuitive understanding of it. We have some pictures that we can draw. And the first thing we will do is to compare lines of different length. We will have a big line and a short line, and it is obvious with our pre-theoretical intuition that the bigger line must have more points than the shorter one. Not so according to Cantor. Suppose that these are the lines AB and CD that we are comparing. The initial idea was that AB must have more points. But now we will construct some more drawings here that will help us define one-to-one correspondence between points of the lines. So we will regard these lines as sets of points. We will extend the lines AC and BD until they intersect at the point that we will call X. Now that we have the point X, we will draw straight lines long enough to intersect both of the horizontal lines that we are comparing. Each straight line will have a point Y where it intersects CD and a point Z where it intersects the line AB. Those points could have been a bit to the left or a bit to the right. But wherever we put them, wherever we draw a line to intersect CD, the point of intersection will be associated to exactly one intersection on the other line. So for each point on the line AB, there is exactly one point on the line C that will go through the point X. And the other way around, and there will be no point left alone, and there will be no point associated to more than one point on the other line. So we have one-to-one correspondence between the lines, between the points of the two different lines. And here we have circular lines. We have two circles, a small one and a large one, and we put them one over the other so that their centers are at the same place. And we will draw radii, and each radius gives us a correspondence between one point on the small circle and one point on the large circle. Each point on the large circle will correspond to only one point on the small circle and the other way around. No point is left alone, and no point is in a group associated to more than one point. So again, we have one-to-one correspondence between lines of different length. And we can even relate a finite line to an infinite line. The finite line is the semicircle above, and the infinite line is the horizontal one on the bottom. It can be extended to the left and to the right. From the center of the semicircle, we will draw straight line. We will draw radii that will intersect the semicircle, and that will be extended to intersect the horizontal line at the bottom. For each point on the horizontal line, there will be exactly one point on the semicircle, and the other one, no point left alone, no point in the group. Again, we have one-to-one correspondence. The points, here we have the same, maybe you would prefer this picture. Each point on the vertical line is using the radii related to exactly one point on the semicircle. The point of these correspondences are that all continua are of the same size. Using such arguments, we can prove that a finite line, an infinite line, a surface, a geometrical body in 3 dimensions, regarded as sets of points, they all can be related one-to-one. Having an uncountable number of points, we can make a continual magnitude of any size whatsoever. So the size is irrelevant. How big a line or a shape or a surface is, it all depends on how we order the points. And we can even order them to have a zero magnitude. We can have a continuum of points and put them all at the same place, and the result will be just one point. Or we can have an infinite line or any geometrical figure. Back to Zeno's argument, what would Cantor say? About the right horn, obviously he would reject the premise. He would reject that points have a finite length different from zero. In the case of the left horn, he would deny the validity. Adding 0 plus 0 plus 0 is not necessarily 0. If we have enough of zeros, so if our zeros are not countable, but they're more, if we have uncountably many zeros, we can get something out of nothing. Whether a line is 2 meters, 2 millimeters, 2 light years, this has nothing to do with the number of points. All these are sets of points that can be mapped one-to-one. Here on these pictures, we have numbers put on a straight line. Obviously, all the lines except the last one have holes in them. So if I have two lines that are composed of rational numbers, and I intersect them, nothing guarantees me that the intersection will not be empty. There might be a hole at the intersection. But when we have a line composed of real numbers, whenever such lines intersect, there must be a common point to them. They're not empty, they're continual. And let me give you some more notions that you can encounter in philosophical literature. So we already mentioned countability and uncountability. Now, cardinality is a measure of the size of a set. The cardinality of the set of days in a week is 7. And that's fine with finite sets. For infinite sets, Cantor had to invite a new kind of number because infinity is not a number in the classical sense. It's not a natural number, it's not an integer, it's not a number at all. If we want to consider it a number, we have to invent a new definition, and that's what Cantor did. We suppose that the set of natural numbers has the smallest infinity, and it has the smallest cardinal number that we call Aleph naught, or Aleph naught, depending on whether you're on the right side of Atlantic or not, or we can call it Aleph 0. We suppose that there is no infinity of some third kind between natural numbers and real numbers, between continuum and countable sets. So we say that the set of real numbers has the next cardinal number, which we call Aleph 1. Is there any other cardinal number? In other words, is there any other infinity different from countable infinity and continuum? To answer, we need the notion of a power set. A power set of a set S is a set of all the subsets of S. An example with a finite set. A power set of the set S defined as containing ABC will contain first the empty set. Remember, we said that what follows from our definitions is that empty sets are subsets of any set. Then we list the subsets. The set containing A is a subset of S. The set containing A and C is a subset of S. And the set ABC, S itself, is a subset of itself. The power set has more members than the original set, which is obvious when we look at the finite sets. Cantor proved, we have no time to demonstrate this proof here, but Cantor proved that this holds for infinite sets as well, that a power set is always of cardinality larger than the original set. So a set of all subsets of set of natural numbers is of a cardinality larger than the set of larger than Aleph 0. So we can make a power set of the set of real numbers. And that set will be of a different cardinality. And we will say that that cardinality is Aleph 2. Then we can make a power set of that one and get a set of a cardinality Aleph 3. And so on without ends. If we follow Cantor's definitions, the set of transfinite numbers is itself infinite. lots of infinities for our feeble minds to understand, let alone to imagine.